Okay, hello there. Are we live? Yeah, we are. Okie dokie. So today we're working on, well, we're continuing the work on the project we started a couple of weeks back. So today we're gonna finally try to connect the camera, which is this, the OV2640 from OmniVision. So this is actually the datasheet of the actual camera, but the module that I have is, I actually had a bit of problem to find some more informations, for example, about the pinout. So this is the only place I found some details about the module itself. So that's what we are going to be using when interfacing with it. So basically that's what I want to at least try to or start at least working on it. So before, in previous streams, we managed to get the communication working between the BlackPill and the Wi-Fi module, the ESP01 module, and we even got some how does it look? Yeah, like that. We even got some commands working, so we are able to more or less communicate with the Wi-Fi module. So we will probably improve this API and the communication method later on at some stage. But in the meantime, I would really like to get the I would really like to look into getting the camera talking to the BluePill, and that's actually going to be a bit of a task. So I don't know how far are we going to get. How far are we going to get today during this stream? But at least I want to do some progress on it. And I don't know if I'll do all of this on stream because I have limited amount of time, and I really want to press on with this. But there's definitely going to be some updates and stuff like that. So regardless how far we're gonna get into it, I'll show what I can about interfacing it. Yeah. So hopefully there's not going to be any issues with audio, because I spent some time setting up the OBS so that I can safely stream with music and then basically strip the music track out of the video. So hopefully it should work fine now. So basically, as you're watching this on YouTube sometime in the future, there's not going to be any music within it, so it should be safe to just upload it in and not worry about any copyrights and stuff like that. And I even got myself some proper thingy here for voice capture, so hopefully the quality should be a little bit better as well. Okay, so I guess we're just gonna start cracking on it. So I did prepare myself a little bit. Basically, I just wanted to not waste stuff on some stupid crap. So basically, I more or less know how I'm going to connect the camera into the chip. So if we're looking at the pinout in here, I would like to hook all those data lines into the one port. So if we look at the BluePill or the BlackPill, I think we will hook up the data ports to the port A, so all the way from A0 to A9 as it is in here. Those two we just gonna probably hard code, or not hard code, hook up directly to the ground and to the 3.3 volt. I noticed this, and we're going to look at this first because basically what it is a master clock that we have to provide into the camera. And when I was looking in here in the data sheet of the sensor itself, the main sensor, it's this clock here. So I was hoping that basically that's going to be provided by the module, but the module that I have doesn't provide any clock, so it's missing a quartz probably crystal or something like that, because it requires a fair bit of frequency. So I think it was somewhere around this, so minimum 6 megahertz, typical 24, so that's a fair amount of clocks that we need to pass into it. And I don't have an easy way to generate this, so I'm hoping that we can use the timer clock, or sorry, use a timer peripheral on the BlackPill to generate the clock, output it into the pin, and then we will use this pin to drive the clock on the camera. So that's the obstacle one that we have to look at. Those guys, we will hook it up to just pins, and I'm pretty sure that we're going to use the EXTI interrupt to read the state on those, because that gives us the synchronization. So basically it gives us the indication when the frame ends and starts, where each row ends and starts. And the pixel clock is basically it shows us when it is ready to read the byte that indicates the pixel value. So I forgot what it is, but basically it's either the negative or positive edge indicates when the data is ready to read, and I think it's also configurable through the I2C. So yeah, and we need to get the I2C working as well. So like I said, it's a fair bit of work, and then we have to agree basically on the method of reading the pixel bytes as well, because that's probably going to be operating at, you know, like at decent speed. I don't know how fast, but presumably, you know, if this guy requires minimum 6 megahertz, so yeah, it's going to be a pretty it's going to, all of this gonna have to run quite fast. So like I said, basically A0 to A9 is going to be our data pins. So that probably means that we can shift the serial port that we have on port 9 and 10, and then we have to agree on where we're going to hook up the remaining pins, those guys, and then the I2C. Okay, so I guess let's just start it. So currently we are using the PA9 and PA10, which is the USART1. So USART1. So let's see the mapping that we have in here. So we only have available, I think, those three anyway. Yes. So we can choose something either higher up. So we cannot use this. So for example, we could use this or find a USART instance somewhere on the B port, for example. But I think that we actually can just use this. So we will swap this to our USART6, RX and TX. So it's just going to be PA11 and PA12. So that will move this up a little bit. Yeah. And then we definitely have a B6 and B7, I think. So that's good. That I think there's a I2C interface on those. And then whatever else we can use for the other pins, provided that there is a external interrupt on those. But I think like we would be very unlucky if we didn't found any EXT pins or EXTE enabled pins. Okie dokie, so let's just turn on some music for myself. Like this. Hopefully it's not going to be too loud. Is it? Okay, I think we're good. Okay, it's a bit too loud for me. Like that. Okie dokie. So, okay, and because we have so many pins all over the place, maybe we should just put some schematics in there. New blank project. So that's going to be Claire. And maybe we should put this in a like that. I don't think I'm going to be building a board for it, but who knows? Is there to F411? I think. What was it? It's 11 CEU. Okay. What have I done? I need to do this. STM32 F411 there. And what did we want it? So we want so we need USART what was it, 6 I think, tx. No, it was here somewhere, tx, and then how do you copy? I forgot. Just a normal, okay. Mode E is edit. So Rx, and those were PA12 and PA11. So 12 is Rx. It was M, yeah. So this and this, okie dokie. I haven't used this in a bit, so I just need to refresh a couple of stuff. Yeah, okie dokie. So then, should we edit it straight away? In here, serial, yeah. So the tx was 11 and 12 was this, and that should be 6, and that should be 6. R6, and this as well. Okay, so now we need the, let's have a look at the I square C. Actually, no, I think I'm pretty positive it's BA6, I think. That's clock, I2C1 SCL, okay. So let's get this all configured. What's B and RB. I2C. So PB6, yeah, that's clock. PB6 is SCL, and then PB7 is SD. Like that. So SCL, it's what, GBRD.PB6 was into alternate like that. Okay, yeah, PB7 SDA. Okay, so PB6 and PB7. So I2C, that was instance 1. SDA. And C1 CL. Okay. So now PPA0 to 9 is going to be the bus. So pixel bus maybe. How do you do the bus? What the hell? How do you do this? Like this and like that. Okay. So that's where we read our data. Okay. So in that case, so this is gone. So now we need the timer output pin for the for this dude. So master clock into sensor. So how many timers do we have there? So do we have a timer one? I don't think so. There's only we do. Okay, so we have a 1, 2, 5, 3, 4, 9, 10, 11. So we have a 1 at PB0. Okay, and PB0 channel 2N, channel 3, P, we don't have an E port here. PB12, PA10, PA10 is available actually. that's 10. Okay, what about 2? So it's PA0 wake up. No, this is all. This is all. We could use this. PA15 is free. It's a channel 1. PB3, we could also use this. Oh yeah, so actually this is better. Timer 1, timer 2, channel 1, PA0. Okay, so let's just use the rest of the port A in that case. And that's all, that's our entire port A used, so it's fine. So that means that we have a little bit more of the stuff on the port B if we need to. So PA15, timer 2, channel 1. So PA15. Like that. So that's timer 2, channel 1. Was it like X clock? CLK, yeah. So we will see how fast we can drive that pin then for the other stuff. So then PA13 and 14 and 10. So we could probably use those for the we can use those for the interrupts, I guess. So was it PA10? Do we have something there that we want to preserve maybe? That's user maybe. No, because then that's a TX, so no. Oh, those guys are the JTAG pins. But it doesn't really matter, actually. B15, B14. Okay, here I have a close then, because all of this is going to be used. Ah, yeah, because not all of those are available in here. So I don't even have a A10. I know, I do have it in here. I don't have a PA13, yeah, because that's hooked up to the JTAG, and 14. Okay, so fuck it. So we will use the B3, B4, and B5, I guess, because those are going to be just between the the USART and the I2C. So B3, B4, and B5. That's also JTAG. Okay, so B8 and B9. Okay, so B7, that's our SDA. B6, so we can use B8, B9, and let's say B5. Because yeah, we're using a fair amount of pins in here. Yeah, let's do it like that. So B9, B8, and then B5. Okay. So what was it? It's vsync. Oops, not V. It's R. So B9, vsync. Horizontal. So that's going to be B8, I guess. Like that, and we need the pixel clock. So B5. Clock. Okie not here. It's here. How to name it? Cam control pins. So that's vsync. Href. Oops. Href and PC. Okay. So that was what? That's 5. That's 8, and that's 9. Href was 9. Href was 8. And that's not going to be inter-alternate, that's going to be yeah, in a second. So that's into input, input open, what was it? F4 XX. How? And we need an API reference. Input, what was it? pull down input, pull up input. Yeah, exactly. So let's have a look at the, we need to look at the diagram. So vsync, it's normally slow, and then the transition to high, and then the high pulse is indicating the new frame. So we want it to be into pull down input. Pull down input, and the same we want for the PCLK, because in the PCLK it's the edge, because you see it's phase shifted. So in here it's either the positive or the negative edge determines the if the data, if the pixel data is valid. And in href it's also the positive pulse. So all of them, they have to be pull down input into pull down input, like that. Into alternate. Yeah, it's complaining about it. That's in a second. So we have this, and then we need to do this for the entire port A as well. Port A is the pixel data port. So PA, well, it's the PD pixel data 0, right? So it's GPIO A dot PA 0, and that's all is, I guess, in pull down. I don't know. We're going to be reading this manually, so I don't think it matters in this case. So into pull down input, raz, dwa, trzy, cztery, pięć, sześć, siedem, osiem, dziewięć, 10. Like that. And this as well. And the reason we do this is because, at least as far as I know, there is no way within any of the halls to read the entire port. I think there's some the guys are working in the embedded hull crate. They're looking to define some sort of trait that will allow to read the entire port data, but for the time being we have to do this individually from each of the pins. So we have this, we have this, we have this. So let's configure the I2C. So for this, we're just going to wrap the example. Is there some I2C stuff here? Do you want me to type it at all by myself? SPI I2C. Oh man. Okay. I2C. Yes, we need self, pins, mode, and clocks. Okay. So let come I2C. So it's I2C. Let's ask compiler for help. Is it I2C? I2C abstraction. What does this do? Okay, so we need the peripheral. It's DP. I2C1. The pins are the I2C. I never remember which one goes first. Like that, and we need the mode. Mode, and what was the mode? It's the mode as in speed. It's this. Oh yeah, the standard frequency hertz. So I think we want fast, yeah. So clocks like that, and then the mode. What was it? Fast. Fast, and then we want frequency, let's say 400. Can I do this? Kilohertz? No. Okay, and duty cycle. I think I can do this. And then the duty cycle is I think this, because I don't really remember. Whoa. New Detroit is not implemented for alternate push-pull. It's not satisfied, blah blah blah. Oh yes. Into alternate, let's have a look. Was it open? It has to be open drain, isn't it? Ah yeah, into alternate open drain, yeah. Open drain. what is it? The trade, blah blah blah, is not implemented for. Are we using the wrong instance? No, I2C1. I2C. I2C1. What am I doing wrong? I2C, this read. So pins is pins, and pins, restore, no, blah blah blah. SCL and SDA. Okay. Okay. Okay, so that compiles. So we have the ports, we have the I2C, we have those guys. So we can get those guys to configure as our EXTI interrupts. So let's do that now. So it's pclk dot what would the command or the API call? XTI. There's this interface that we need to look at. EXTI pin, yeah. So make interrupt source, trigger, enable, blah blah blah. So make interrupt source. Make interrupt source. So we need sysconfig. Where do we get the sysconfig from? That was from the RCC, yeah? RCC dot no TP sysconfig like that. Reference mod. Oh yeah, because we need the object. Okay, so let's expose this in here. So let's CFG, so that's dp dot sysconfig, and I think it was, yeah, and I think this has to be mute, so then we can sysconfig. Okay, so we need to make interrupt source. We need the, yeah, and we need to define how we want it to trigger. So we have to go back here and have a look again. So I'm not sure which one is the default. So using the COM10 piezo output can be guided by the active blah blah. What? The default edge for valid data is the negative edge. So we want to trigger on the pulse down, and there should be a way to do this edge. So it's falling. So edge falling. So trigger on edge. Yeah. Oops. Trigger on edge, and we need to pass in this guy again. This is config and then edge for. I don't know how to change it so that it updates the imports instead. Oh wow, I do not need this here. We need EXTI? No, I think that's in the GPIO, is it? Edge. Do we need something else? No, we don't. Okay. So edge falling. What do you want? Oh, we want EXTI. Okay. So dp EXTI like that. So trigger on edge. Trigger on edge falling, blah blah blah. Cannot borrow as dp is not declared as mutable. And we need to do the same for those guys as well. And here as well. It's href like that, and vsync. Yeah. And now we need to do the EXTI handler, interrupt handler as well. So we need to find out which EXTI, because there's a range of pins that we can assign the handler. Interrupt. We're looking for the enumeration, this. So there. Okay, so we're looking at the two ranges in that case. 9 to 5, there it is. And that's actually ideal. I should have actually thought about it when we were assigning the pins. Because we were just lucky in here that we decided to use those 5, 8, 9. Because otherwise we would have to set it in two separate handlers if we went outside of this range. Okay, so it's EXTI9 to 5. We don't know what we're going to pass in here yet. So there. So EXTI95 and EXTI95. Whoops. Maybe we can just put here some notification. So EXTI trigger like that. Okay, so that's that for now. And now we need the, like I said, we need the pin that we will use for driving the X clock or whatever it's called. And we will need this for later as well. Okay, so we decided to use what? PA15, and I think here we are going to get into a problem, because what I want to use is something called output compare, and I've tried to use this in the past in a couple of smaller projects that I've done. So basically, what was it? So basically it's output compare, output compare mode. So basically in here we are configuring the timer. You know, we preload our values into the registers to, you know, to get the you know, the what the word I'm looking at, to trigger period, to basically to clock at the rate that we wanted. But instead of generating an interrupt, although we can do this as well, we have an option in here to pass in the trigger into a pin. So that's why, for example, in here, so that's why there is a, for example, a specific timer channel associated with the pin. So, you know, it's pretty common to use this with the peripherals like PWM. But we can also, instead of just utilizing the PWM, where we can directly drive that pin and change the period, the duty cycle, stuff like that, in here we tie this directly to the timer peripheral, and then the timer peripheral on overflow will drive the pin up or down. And then again, the up or down, it depends on the configuration. But in our case, we want to use the option called toggle. We will see probably in the registers later on. There's an option to toggle the pin. So essentially, every overflow, it will drive it high, and if it's high, low, and so on. So basically, I wanted to use this. But if we look at the API, there is nothing compare. Is compare pools. Okay, so maybe there is some. Maybe something has. Maybe something has changed, but no, because all of this is coming directly from the pack. So let's say timer 1. No, not pack. Team. No, that's pack as well. So all of this is just allows us to start the timer, you know, maybe configure some PWM, configure some trigger or the interrupts. But we have no way to redirect this into the pin directly. And as far as I understand, neither the STM32F1 crate has it, nor this. And to be honest, those are the only two that I'm semi-familiar with. So basically what we will do is we will take this pin, we will trigger the interrupt, and we will drive it in our interrupt handling routine. So in here, was it timer 2? Team 2? No, what's the interrupt? Just team 2. Okay, so then for that we will need the timer output, timer 2 output channel, is it 2? Channel 1. Why I don't remember those things. So let PA team channel 2 and GPIA and PA15 and into for this we need like a push-pull. Push-pull into push-pull output. Like that. Okay, let me just restart the music. What do we want? Yeah, maybe this. So John Carpenter inspired retrowave. Okay. Okay, so we need this, and we will be driving this only within the interrupt routine. So we will push it in or pass it in here. So like that, and that's going to be pin output push pull. So pin output push pull. Like that, and we need in here as well. So we need pin, we need output, and we need push pull. Like that, and it's yeah, it needs some more stuff. So that's a character and the number. So this is port A and it's a pin 15. Yeah. And now we need to pass it in here. So team 2 channel 2. And then in here it's a local and it's a team 2 channel. Why I keep writing channel 2? It's channel 1. Is it? It is. It's channel 1. There. Yeah. And then once we have it in here, it's ctx dot local dot this dot toggle. Oh, but we need the timer structure as well, which we haven't even configured. So we need so let timer 2 equals timer 2 new. So actually we can do this easier. It's dp dot team2 dot counter hertz, because we want it to run at 6 megahertz at least. So like that, and that needs counter hertz. Okay, so I'm doing this wrong. I forgot what the API was. Hertz, yeah. Oh, it just needs clocks, and we pass this to the start, I think. Like that. Yeah, and then timer 2 dot what was it? Listen. It's event. What was it? Update. Update. But first we need to start it. So timer 2 dot start. Yeah, and here we pass in the rate. So 6. Like that. And we need the event. Oh, it's colliding. And as usual, and this is what unused result. Once we have our stuff working, I promise we'll look after all of those error handlings. Okay, so maybe we should start trying to load this in here. So hopefully we should get the timer interrupt triggered in here. So cargo watch this. Okay. So that works. But it would be nice to see it on some sort of physical device. So I actually should have a logic analyzer somewhere here. Like that. So you just need to give me a couple of minutes, just set it up. So we need this, and we need the ground, and we're spitting it into the PA15. Okay. sure if that will work. I haven't used this in a while. Can you guys see this? Okay. So channel 1, that's actually perfect. Can I just run this? Okay, so let's first here, let's make sure that it's actually working. So it's spitting in here. But there's nothing here, but we're dying. Why is that? An error occurred during capture. Could it be the buffer size? Yeah, I had problems with this in the past. Let's see what sort of... So we're running this at 6 megahertz. So we need at least twice as much to capture it or to sample it. Because of what? What's the theorem? So ideally, if we could capture at 24, that would be great. Yeah, that's not gonna work. So we need a large buffer to capture it at that speed. Yeah, no, it keeps crashing. It could be because I have so many things on the USB. And I do have oscilloscope, but I would need to set it up as well. This logic analyzer is just a cheapo from the internet or from yeah. So I don't expect, like, it was usually fine for my little hobby stuff. Let's try. Okay, so let's see if one is capturable. Okay. Nope. I'm clicking too many things. Like, I don't have a reason. Actually, I do have a reason. Like, this is definitely incorrect because we're not clearing the interrupt. So hold on. Okay, let's first fix that because that's definitely wrong. Because we forgot to pass in the timer interrupt or the timer to our interrupt handler. So again, so timer 2, so it's timer, no, it's, we're using the countdown timer, so that's different. So counter, no, what was it, counter hertz, what does it give us? Counter hertz and just a team. So in here we need this, and that's our counter hertz, and that's team 2. Like that. This, we're gonna kill it for the time being. Missing timer. Like that, and we need timer 2 here as well. Okay, so let ctx dot local dot timer 2, right? So we need team dot unlisten. It's team event update. We need team dot, we need to clear the interrupt. Team event update, and then we need to listen again. Like that. Okay, and let's have a look now. Yeah, this dude is not gonna. I don't think we will have much luck with this guy. Not sure if we're going to be able to capture those. It would be nice though. If that's a massive buffer, I would. Yeah. Okay. Maybe I'll try to take out the oscilloscope. Oh shit. I have it connected to the wrong pin. Damn it. Boom. That's better. Okay. Like that. So we're driving it. Oh. That's not 1 meg. Hmm. That's Jesus. What is it? Sys clock. Yeah, I want it at 100 megahertz or. Yeah, I want at least that. Oh, that could be because of this. Like printing to the console, it could be affecting it. That's happening in the idle loop. It's from our previous stream. Okay. Okay, that's better. That's what we wanted. So how fast we're? It's 8 megaseconds. What is it? Mega samples per second. So let's try. I don't know, 18. And let's try to do it at 6 megahertz. this. Oh. Okay, so that's going to be problematic, I think, because the interrupt is taking over all of the functionality. So if you see here, we had init, but we're not executing the idle at all because we're running so fast. So I don't think this is going to work. Because we keep triggering the interrupt, and the microcontroller doesn't have time to handle our other tasks. And that's why I wanted to have the possibility of just simply utilizing the hardware directly, so without the handler interrupt. Okay, so one other option that we have, but I'm not sure if that's going to work, and I'm not sure if we're wasting time, even possibly, is that we could try to go down or dirty right into the unsafe territory and just see if we can manually configure the output compare. And actually, I don't think, actually that probably wouldn't even be all that much work. Let's just kill this, because I think what we need in this case is we won't need this either, I think. So all we need to do is, so unsafe oh. So let team raw, we need to, I might forget the syntax, so I think it's team 2, it's pt1, so that allows us to grab the reference to the timer, and then we need to just find out we need to find out the what I'm looking for, the word, the registers responsible for configuring the output compare. So this function is used to control an output. So procedure, select the counter clock. So we have that. We have that because that's handled in the start. That basically configures our overflow period. So we need that's if we're using the DMA. So we need OCM to toggle. So we need OCM. OCXM. We're back here. Or is it OC? 1M, yes, 1C, 1M. So capture compare mode register. This bit field. CC2 channel as input, as output. OC1CE, OC1M. So we need to push in 0, 1, 1 in there, and then we need to enable it. Okay. So then, so hold on. This, I don't want this for now, but I want to be able to see what's going on. So raw dot there. This is for the input compare, this is for the output compare. We're looking for modify. This is, we're not going to be reading, we will be writing. The register is OC1M, and then we need to find a way to, oh, this is nice. See, because I thought that we can actually do this, just take bits and then pass in the 0, 1, 1 value. But look what's happening here. It actually provides you aliases for all of those configuration options. Oh, that's nice. I actually forgot. Oh, well, I didn't know that it went that far. Okay, what's this? No method name found for raw pointer. Yeah, because this is like that. Okay, there it is. So it's toggle, and then we need to find the enable register. It's been a while since I've done this. This is the bad thing about using hulls of different kind, because it kind of makes you lazy. So basically there has to be a way to enable the output onto the pin. It was like CR1, no. It's like CC, what? Actually, no. CCMR, CC capture compare enable register. That's what we want. No, what I've done there. CCR, CCER, R. there. Oh, it's not here. There it is. So we are on channel 1, output enable, so we just need to put on it. OC1 signal is output on the corresponding output pin depending on, so CC1E. And again we need to modify. Come on. Modify, and again we don't read, we just write, and it's write dot CC1E, and we want to set bit. Holy shit, we just went right into the guts of microcontroller and we toggled some bits. Okay. Logic. And nothing. That's because we are being silly, and this is push-pull output, and because we're using this as a timer, we need to configure it as the okay, but man, so this is another problem, because now we need to turn it into alternate. We need to turn it into alternate, but there's no support for output compare, so our alternate is not gonna work, because if we look at the here into the GPIO, where is it? API convert alt. There's going to be stuff like useart, I2C, but it's not can even. There's not going to be a support for the output compare. SPI. Useart, yeah. So that means we need to configure this manually as well. So let's clean this up first. So we actually don't need this nor this. Okay, I knew that we shouldn't even, because usually when you start messing, it's mess all the way down. So how do I do this? I need to turn this into probably like push-pull output. There should be something in here. No, it's going to be alternate, is it? AF01. So output compare. How do I need to configure the pin for output compare? The update event has no effect, blah blah blah. Can I just simply take it and just modify it as the just modify it as the alternate? What I'm doing. So raw let raw PA15 no, it's not, because we're grabbing the whole port. So GPIOA and again we need it's GPIO GPIO PTR and we need to configure the what's the AF01. So AFRL. Okay, yes, because they were two registers for this. So you configure the lower one for the pins 0 to 7, and you configure the higher one for the above. So if we're configuring the port 15 or the pin 15 of the port A, we need to edit this, and we know from this table that the alternate functionality for channel 1 timer 2 is AF01. So that means in here we need to configure it as 0001, just the top 4 bits. So the most significant nibble of that register. And we only configure the AFRH. So raw GPOA was it AF what do I have here? Okay, that's just gives me rubbish here. AFRH it's AFRH and then dot modify. Nothing, right. Yeah, I think our thingy got totally confused. Let's give it. Let's allow it to recompile. Okay. Not found. Ah, that's why. Okay. Okay. So it was us. I'm sorry. We need GPO A from pack. GPIO. So W dot, yeah, there it is. So that's this, and then the bits is, oh, even better. Simply AF1. And it works. At least this, the other stuff. Like, I'm a little bit scared that if we're not, well, we're only doing this once during the initialization, so I think we're safe here. It would this probably wouldn't be that good to do in one of the tasks, because then we're getting into the concurrency issues. Because what we're doing in here, or we might get into the concurrency issues, because what we're taking here is that we're grabbing a raw reference to the register and modifying it. So we will have to ensure somehow that we're not, we're not modifying something that can be read or written to in some other task, for example. But since we're doing this in here, in just the initialization method, I'm pretty sure that this is just one thread. So I think we're fine here. Okay, so, and it works. We're almost at even the required frequency, 6. And it's still sending, so we don't have the issue with the interrupt where it's starving our idle loop. So we are kind of achieving what we want. So okay, so that's cool actually. That's cool. Okay, so I just want to make sure that it's actually running. So boom, that's our idle task. As in, yeah, our idle task. So that's currently, I don't have the Wi-Fi module plugged in, so it's sending. So in fact, that should fail probably because there's nothing to receive it. But okay, that's a different issue. What this shows me is that our idle task is working and our 6 megahertz generation in here, which still runs, okay, but anyway, that works. So that this is being driven directly by the peripheral, so outside of our task or idle loop. So I'm happy with that. So maybe I could think about trying to maybe push it into the crate as some sort of API for using the output compare. Okay, I think I'm actually a little bit running a little bit late because it's been what, 2 hours again. It's the magic cutoff time for me. So okay, I think we have some sort of progress. So basically what we want to do now is we need to test those, that those are triggered whenever we have a new frame, new row, blah 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 blah. See if we can read some of the data from the camera. We need to use the I2C to configure the camera, because what's horrible in here is when I read this and then it's sensor unit the basic blah 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 blah. So there's a sample config for Arduino for the I2C configuration, and it's massive. So we're gonna have to analyze what it does. We're gonna have to compare it with the registers that are documented in here. This is our I2C registers within the camera module that we can use to configure our outputs. So then we need to get the camera going with the I2C. There's probably going to be some obstacles along the way in there as well. And I think we can be able to then read some frames out of that. And that doesn't even bring us close to the finish line, because we still have to get something on the on our host machine to capture the images and to write it down, or to even generate the stream out of that we can view. Okay, but I guess it's bye-bye for the time being.